These are the calculated problems for the unit on optics. There are actually very few because the author provides very few in those optics chapters. So few that I actually added a couple. You'll see that later. So let's get started here with the first one, which is chapter 26, number 5, which says the nearest star beyond the Sun is Alpha Centauri. And Alpha Centauri, actually it's Proxima Centauri, but there's not much difference. 4.2 times 10 to the 16 meters away, times 10 to the 16 meters. If we were to receive a radio message from the star today, how long ago would it have been sent? So that means we have to deal with the speed of light, which is around at 3 times 10 to the 8 meters. And we have to divide the two numbers. Give me a moment here. There we go. There's the fraction bar. Oops, and then I made a mistake. Great. There we go. Meters per second. So this is the speed of light. Of course it is 299,700, I believe, kilometers per second, but we round it to just two significant figures because that's what is given for the distance to Alpha Centauri. And then of course from kilometers to meters, that's then 300 million or 3.0 times 10 to the 8. That is the time it took for the light to get to the solar system. We can do this just about in our heads. 4.2 or 42 divided by 3. 42 divided by 3 is 14. There we go. And then shift the decimal point 1.4. 4.2 divided by 3.0 is 1.4. And then the exponents is 10 to the 16 divided by 10 to the 8, which is 10 to the 16 minus 8, so 10 to the 8. And the unit, of course, comes out to, the meters are canceling, and it's divided by second, so that second goes to the top. Let me show you that on the graphing calculator. 4.2, 10 to the 16, divided by 3.0, 10 to the 8th, because I will give you some numbers that you may not be able to do in your head. And here you go, that's the 140 million that I mentioned, so 1.4, 10 to the 8th. Now we probably don't want to express that number in seconds, 140 million seconds, so what we do is we divide by how many seconds we have in a year, and that would be 3,600 seconds in an hour. Divide by 24 hours in a day. And divide by 365.25 days in a year. And when you do these, then the seconds would cancel, the hours would cancel, the days would cancel, and what remains would be years, where you divide and divide, so you're going to have years in the numerator. And again, when I do that on the graphing calculator, divide by 3,600, divide by 24, divide by 365.25, 4.43, or around it 4.4 years. Chapter 26, number 10 says, a ball with the same diameter as a light bulb is held halfway between a bulb and a wall as shown in the sketch. Construct light rays, similar to those in the previous figure, and show that the diameter of the umbra on the wall is the same as the diameter of the ball, and that the diameter of the penumbra is 3 times the diameter of the ball. So for the umbra, what I'm going to do is I'm going to take from the top of the lamp to the top of the ball, straight across to the wall, from the bottom of the lamp and the bottom of the ball straight to the wall. Maybe I shift that a little bit down. There we go. And in between I have the umbral shadow, because none of the light from the bulb will reach the wall in this area. Then go from the bottom of the ball to the top of the ball and towards the wall. There we go. Now here, some of the light in this area here, some of the light is blocked out from the bottom of the lamp, but there's also some light getting there from the top of the lamp. So that's why there is some shade here. It's not completely bright, unlike outside of the line here on top, for example, where all the light goes to. But the ball does block some of the light from the lamp, from the lower portion of the lamp, but permits light from the top portion of the lamp to get to the wall. So that's why we have not complete darkness here and not complete brightness. And then really the same thing happens at the bottom. So top of the lamp, bottom of the ball, towards the wall. And of course the same reasoning, that it's not that dark but not totally bright either. And just like they said, the diameter of the umbra on the wall is the same as the diameter of the ball, and the diameter of the penumbra is 3 times the diameter of the ball. So if we assume that this is actually a circle on the wall, we're looking at it in cross section here, then the diameter would be from the very top to the very bottom. It's 3 times the size of the ball. The real one for our sun and the moon is a whole lot smaller than the sun, and only from our perspective on Earth it looks like they have the same diameter, but that's because the much larger sun, approximately 400 times larger sun, is also 400 times further away, so they look the same size. But because the moon truly has a smaller size than the sun, the umbral shadow is smaller, and the penumbral shadow is also smaller, but the principle is the same. You have kind of a light area, not completely dark but not completely light, around the totally dark area of a total eclipse.